I believe the examples and exercises has given us a solid understanding on magnitude of vectors, scalar multiplication, unit vectors, and the likes, including addition and subtraction of vectors. Now, I want to go into a new segment called direction cosine. Now, this is a segment that involves evaluating the direction of a vector with specified angles with respect to the axis of reference. Okay, now the direction of a vector is determined by the angles the vector makes with the axis of reference. Okay, now we have two-dimensional vector here. We also have three-dimensional vector here. So we want to understand the concept of direction cosine. Now, we call it cosine because the trigonometric function we are using here is a cosine function. And if we go from the principle of SOHCAHTOA in trigonometry, we understand the sine is opposite over the hypotenuse, the cos is adjacent over the hypotenuse, the tan is opposite divided by the adjacent. Now, with that done, we can then establish the principle of direction cosine for a two-dimensional vector. Now, with this, the column vector for R, let's call this R1, or just say R. The column vector for R here is equal to xy because it is x on the x-axis, y on the y-axis, and if we write it in terms of unit vector, we will have xi plus yj. Okay, now we want to evaluate cos alpha and we also want to evaluate cos beta. Following the principle of trig, we understand that cos is equals to adjacent over the hypotenuse. When we are considering the alpha here, angle alpha, the adjacent is x and the hypotenuse is r. However, we will not just be using r, we will be using the length as the magnitude of r. Similarly, cos beta, when we are considering angle beta, the adjacent to angle beta is y. Okay, this is the opposite, this is the adjacent. That's for angle beta. So with that done, we can say that cos beta is equals to y divided by modulus of r. Now we can call cos alpha to be equals to L. We can also say let cos beta be equals to m. And therefore, we have a final conclusion that L squared plus m squared is equal to 1. This is for two-dimensional vectors. Now we are just laying the foundation. Let us also move to a three-dimensional vector. Now let's look at this three-dimensional vector. We want to evaluate the direction cosines for both x, y, and z axis. The column vector for this vector here, for vector r, will be x on the x-axis, y on the y-axis, and z on the z-axis. And if we write it in terms of unit vector, we'll have xi plus yj plus zk. Now moving on, we want to evaluate cos alpha, we want to evaluate cos beta, we want to evaluate cos gamma. And we know that cos is equals to adjacent divided by the hypotenuse. And the hypotenuse in this case is also modulus of r. So considering alpha, the adjacent is x. So that will be x divided by omega r. Considering beta, just like we had in the two dimension, the adjacent is y. And that will be y divided by modulus of r. And considering gamma, the adjacent is z, and that will be z divided by modulus of r. Now, just like we did in two-dimensional vector, we can say this is equals to L, this is equals to M, and this is equals to N. Therefore, we can come to a conclusion that L squared plus M squared plus N is equal to 1. Now, let's bring it all together as 1. In two-dimensional vector, we have that R is equals to xi plus yj. Therefore, if we are asked to evaluate the direction cosine, that means we are talking about cos alpha on the x-axis and cos beta on the y-axis. We call cos alpha to be equals to L, cos beta we equate it to M. Cos alpha, as we have seen here, is equals to x divided by the modulus of R. X divided by the modulus of R, and cos beta will be y divided by the modulus of R. So alpha x beta y, and we can come to a conclusion that L squared, okay, plus M squared is equals to 1. Similarly, if we have, let us bring this here. Similarly, if we have a three-dimensional vector of R is equals to xi plus yj plus zk. We can evaluate the direction cosine on the x-axis to be cos alpha, direction cosine on the y-axis to be cos beta, and direction cosine on the z-axis to be cos gamma. We call this L, we call this M, and we call this N. Now alpha is related to x-axis, and if you see here, you can see that it is x divided by modulus of R. Beta is related to y-axis, that will be y divided by modulus of R. Gamma is related to the z-axis, that's z divided by the modulus of R. And we can come to a conclusion that L squared plus M squared plus N squared is equal to 1. Now this is the whole deal in direction cosine. So let's take an example on 2 dimension. Let's also take an example on 3 dimension. Let's begin. We are asked to evaluate the direction cosine of a 2-dimensional vector for R1 to be equal to, or let me just say A. Let's take R. R is equals to 9i minus 2j. 9i minus 2j. And if you want to implement this now, all we just have to do is, we know that 9 is equals to x and minus 2 is equals to y. Okay, so with that done, we can evaluate the modulus of R. The modulus of R in this place will be equals to the square root of 9 squared plus minus 2 squared, which I believe you are familiar with the process. So this will be just the square root of 81 plus 4, which will be root 85. Now we can evaluate cos alpha. We can also evaluate cos beta. Cos alpha is related to the x-axis, so it will be x divided by modulus of R. Cos beta is related to the y-axis, so it will be y divided by the modulus of R. So this is L and this is M. Now cos alpha is x divided by modulus of R. So the value of x coefficient here is 9. 9 divided by the modulus of R is root 85. Similarly, the direction cosine on the y-axis is cos beta, and that's y divided by modulus of R. The y value is minus 2, negative 2, and the modulus of R is 85. And this will result into 85. Now, if we use our calculator to prove that L squared plus M squared is equals to 1, we can have that 9 divided by root 85 all squared plus minus 2 divided by root 85 all squared. We want to prove that this is equal to 1. So we now have that this will result into 81 divided by 85 plus 4 divided by 85. So if you use the LCM, this will result into 81 plus 4 divided by 85, 85 divided by 85, which is equal to 1. Now with this example, we have been able to evaluate the direction cosine, that's cos alpha on the x-axis, direction cosine cos beta on the y-axis. This is for a 2-dimensional vector. Now let's try for a 3-dimensional vector. We are asked to evaluate the direction cosine for the vector r is equals to 3i minus 2j plus 6k. 3i minus 2j plus 6k. Now let us evaluate the modulus of r. The modulus of r in this case will be 3 squared plus minus 2 squared plus 6 squared. So this is equals to the square root of 9 plus 4 plus 36, which means that the modulus of r is equals to root 49, which is equals to 7. According to our summary here, we can say that the direction cosine on the x-axis is cos alpha, which is equals to x over modulus of r, similar to the y-axis and z-axis. So let's implement that. Direction cosine on the x-axis is cos alpha, which is the x coefficient divided by the modulus of r. Direction cosine on the y-axis is cos beta, which is the y coefficient divided by the modulus of r. And similarly, direction cosine on the z-axis cos gamma, okay, which is the coefficient of z divided by the modulus of r. You can call this L, M, and N. So this means this is equal to x is equals to 3, y is equals to minus 2, and z is equals to 6. So this direction cosine on the x-axis will be equals to 3 divided by modulus of r, which is 7. Direction cosine on the y-axis is y, as cos beta is y is minus 2 divided by the modulus of 7, modulus of r, which is 7. And finally, for the z-axis of gamma, which is 6, okay, divided by 7. So if you evaluate that L squared plus M squared plus N squared, that means we're saying 3 divided by 7 squared plus minus 2 divided by 7 squared plus 6 divided by 7 squared. What will be the result? So this will give us 9 divided by 49. This will give us 4 divided by 49 and 36 divided by 49. Taking the LCM, we have 9 plus 4 plus 36 divided by 49, which is equals to 49 divided by 49, which is equals to 1. Now, we have evaluated direction cosine on the with 3-dimension vector and also 2-dimension vector, and this is the summary of it. Now in the next lesson video, we'll have an exercise to ensure that we have understanding as regarding this concept of direction cosine.